What if everything you see, touch, and experience the warmth of sunlight, the weight of a book in your hands, even the vastness of the night sky isn't really there? Or at least not in the way you've always believed. Picture this: the entire universe with all its galaxies, stars, and the very fabric of space and time might just be an elaborate illusion. A cosmic trick of the light, projected from a hidden two-dimensional surface we can't even perceive. This isn't science fiction. It's a radical idea born from the cutting edge of theoretical physics, known as the holographic principle, and it could rewrite everything we thought we knew about reality. Think about a hologram for a moment. You've probably seen one shimmering on a credit card or a concert ticket. A flat surface that somehow creates the uncanny illusion of depth, of something three-dimensional popping out at you. Now stretch that idea to the scale of the entire cosmos. What if our universe operates the same way? What if the richness of 3D space, the texture of your skin, the scent of rain, the dizzying expanse of the ocean, is nothing more than information encoded on a distant, invisible 2D boundary? It sounds impossible, almost absurd, yet some of the brightest minds in physics have spent decades wrestling with this very possibility, and the implications are staggering. The holographic principle didn't emerge from thin air. It grew out of the deepest mysteries of black holes, quantum mechanics, and the quest to unify the laws of physics. Scientists like Leonard Susskind and Gerard T. Hooft began asking, what happens to information when it falls into a black hole? Does it vanish, or is it preserved somewhere, somehow? Their answers led to a shocking revelation. The information might be smeared across the black hole's event horizon like invisible ink on a cosmic ledger. From there, the leap wasn't far. If a black hole's insides can be described by its surface, could the same be true for the universe itself? That's the question we're about to explore, one that blurs the line between science and philosophy, between what we know and what we dare to imagine. Buckle up, reality is about to get a lot stranger. The holographic principle turns our perception of reality inside out. Imagine the universe as a movie theater. Except instead of watching images on a flat screen, you're immersed in the film, convinced everything around you is three-dimensional. Now, what if the projector isn't hidden in the back of the room, but etched onto the walls themselves? That's the essence of this radical idea. All the information that makes up our seemingly 3D world, every star, every atom, even the fabric of space-time, might be encoded on a distant two-dimensional surface, like an unfathomably complex cosmic blueprint. The three-dimensional reality we experience could be nothing more than a shadow cast by this underlying 2D code. This isn't just speculative philosophy, it's grounded in cutting-edge physics. Leonard Susskind, one of the pioneers of string theory, realized something astonishing while studying black holes. When matter falls into a black hole, it doesn't just disappear. According to the laws of quantum mechanics, information can't be destroyed. Susskind and Dutch physicist Gerard T. Hooft proposed that this information isn't lost inside the black hole's depths, but is somehow preserved on its surface, the event horizon. Think of it like a cosmic hard drive. Everything that falls in leaves a data imprint on the horizon's edge. This led to a wild extrapolation. If a black hole's interior can be described by information on its boundary, could the entire universe work the same way? The math behind this idea comes from something called the ad/CFT correspondence, a theoretical framework that ties together two seemingly unrelated branches of physics. On one side, you have gravity and the warping of space-time described by Einstein's general relativity. On the other, you have quantum field theory, which governs the behavior of particles. The ad/CFT correspondence suggests these two worlds aren't separate, they're dual descriptions of the same reality. A complex, gravity-filled universe like ours could be perfectly mirrored by a simpler, gravity-free theory operating on its boundary. It's like discovering the entire plot of a novel is hidden in barcodes on its cover. What makes this so mind-bending is how it upends our intuitive grasp of space. We're used to thinking of dimensions as fixed. A line is one-dimensional, a sheet of paper is two, our world is three. But the holographic principle suggests higher dimensions might be emergent, like a mirage. A hologram on your credit card creates the illusion of depth, even though it's just a flat surface with light bouncing off it in precise patterns. Similarly, our 3D universe might be a projection, with all the real information stored on a hidden 2D layer we can't see. The chair you're sitting on, the air you're breathing, everything you perceive as solid and tangible might be pixels in a cosmic display, a trick of the data. This raises profound questions. If the universe is a hologram, what's the projector? Could we ever detect this underlying code, or are we forever trapped inside the illusion? Some physicists speculate that if the principle holds, there might be glitches, tiny inconsistencies in the fabric of reality where the 2D scaffolding shows through, like a screen tearing in a video game. Others argue it's less about literal dimensions and more about how information defines existence. Either way, one thing's clear: the deeper we probe the nature of reality, the less it resembles the world we thought we knew. Stephen Hawking once shook the foundations of physics with a deceptively simple question: what happens to the information that falls into a black hole? In the 1970s, he made a startling discovery: black holes aren't entirely black. They leak. Slowly, over eons, they emit a faint glow of particles now known as Hawking radiation. But here's the catch: Hawking's math suggested that as the black hole radiates, it shrinks and eventually vanishes. And if the black hole disappears, what happens to all the information? The stars, planets, even atoms that once fell inside? According to quantum mechanics, information can never be destroyed. So where does it go? This contradiction, dubbed the black hole information paradox, became one of the fiercest debates in modern physics, setting the stage for a revolutionary idea: the holographic principle. For decades, physicists wrestled with this paradox. If Hawking was right, the universe had a serious problem. Information was vanishing into thin air, breaking one of the most sacred laws of quantum theory. But in the 1990s, two bold thinkers, Gerard T. Hooft and Leonard Susskind, proposed a radical solution. What if the information wasn't truly lost? What if, instead of being crushed into oblivion inside the black hole, it was imprinted onto the event horizon, the point of no return? Picture the event horizon like a cosmic hard drive. Every particle, every shred of data that crossed it might leave behind a kind of quantum fingerprint. Instead of disappearing, the information gets smeared across the surface, encoded in unimaginably tiny pixels of spacetime. This wasn't just a clever workaround, it hinted at something far bigger. If a black hole's interior could be fully described by information on its boundary, maybe the same was true for the entire universe. Think of it like a holographic sticker. The three-dimensional illusion you see is just light bouncing off a flat, encoded surface. T. Hooft and Susskind's insight suggested that reality itself might operate the same way, that the depth, texture, and motion we experience could be a projection from a hidden two-dimensional code. But how could this possibly work? The key lies in the mind-bending math of string theory and something called the add-s/CFT correspondence. Without diving too deep into the equations, imagine two completely different rulebooks for describing the same phenomenon. One describes gravity warping space in 3 dimensions, while the other describes particles interacting on a 2-dimensional surface. The holographic principle claims these rulebooks are secretly the same, that the 3D universe we perceive is just a different way of reading the 2D data. It's like realizing a symphony and a painting could, in some strange way, be two expressions of the same underlying masterpiece. This revelation doesn't just solve the black hole paradox, it rewrites our understanding of reality. If true, the holographic principle means the universe isn't built like a scaffold, with space and time as rigid, fundamental structures. Instead, space might emerge from something deeper, like a 3D mirage rising from a flat desert horizon. That book in your hand, the screen you're watching right now, they might not be solid objects in the traditional sense, but intricate patterns woven into the fabric of an underlying cosmic code. And if that doesn't make you question everything you see, well, just wait. The implications get even stranger. String theory might sound like science fiction, tiny vibrating strands of energy replacing particles as the fundamental building blocks of reality. But it's a serious attempt to solve one of physics' biggest headaches, unifying gravity with quantum mechanics. And here's where things get even wilder. Those hypothetical strings don't just wiggle in the 3 dimensions we know. They vibrate in as many as 10 or 11, curled up into shapes so small we'd never notice them. These hidden dimensions are described by intricate geometric forms called clarifies manifolds, structures so complex they look like cosmic origami folded into the fabric of spacetime. But here's the kicker, those extra dimensions might hold the key to understanding how a 2-dimensional boundary could encode our 3-dimensional world. Imagine plucking a guitar string. The pitch you hear depends on how it vibrates. Tighten the string, and the note gets higher. Now, picture those vibrations happening not just back and forth, but in multiple dimensions, their frequencies determining everything from the mass of an electron to the force of gravity. String theory suggests that what we perceive as particles are just different notes played by these tiny cosmic strings. But if those strings are dancing in higher dimensions, why does our reality feel so firmly 3-dimensional? That's where the holographic principle comes crashing in like a revelation. The math of string theory reveals something astonishing. When you model certain higher dimensional string environments, especially those with negative curvature, like anti-de Sitter space, their physics can be perfectly mirrored by a simpler theory operating on their lower dimensional boundary. It's as if the symphony of a 10-dimensional universe could be transcribed sheet for sheet into a 2-dimensional score with no loss of information. This duality, known as the add-s/CFT correspondence, isn't just a neat trick. It suggests that the extra dimensions string theory proposes might not be real in the way we assume. Instead, they could be emergent, like the illusion of depth in a hologram, rising from interactions on a distant, flatter surface. Visualizing this isn't easy, but think of a shadow puppet show. Your hands twist into shapes: a dog, a bird casting silhouettes on the wall. The 3D movement of your fingers creates 2D images that tell a story. Now scale that up to cosmic proportions. The clarifies manifolds of string theory might be like those twisting hands, their hidden dimensions projecting the physics we experience in our familiar 3. The holographic principle takes it further. Maybe the entire universe is the shadow, and the real action is happening on some unimaginable 2D screen at the edge of everything. This isn't just theoretical sleight of hand. Physicists have used this duality to solve problems that were previously intractable. For example, studying the behavior of a black hole in 5 dimensions might be impossibly complex, but its holographic counterpart, a hot, dense plasma on a 4-dimensional boundary, can be far easier to model. It's like translating an untranslatable poem by rewriting it in another language where the rhymes just click. And if the math holds, it implies something profound. The universe might not have dimensions in the way we think. Instead, dimensionality could be a kind of illusion, a side effect of how information is organized at the most fundamental level. So where does that leave us? If string theory's extra dimensions and the holographic principle are 2 sides of the same coin, it blurs the line between what's real and what's just a convenient way to describe reality. Are we living in a higher dimensional universe, or are those dimensions just a mathematical tool, shadows cast by a deeper, flatter truth? The unsettling answer might be both. The holographic principle doesn't erase the richness of our 3D experience. It just suggests that, like a masterpiece painted with a single thread, reality might be woven from something far simpler than we ever imagined. And if that's true, the next question is even more dizzying. What or who is holding the brush? The AD/CFT correspondence is like finding a secret passage between two entirely different worlds, one ruled by gravity, the other by quantum forces. Picture a sprawling 3D universe, warped and curved by the relentless pull of massive objects, described mathematically by anti-de Sitter space, or AD/S for short. This theoretical playground is drenched in gravity, where black holes loom and space-time bends like taffy. Now, imagine peeling back the curtain to reveal something astonishing. Every event, every particle collision, every ripple in this gravity-filled cosmos has a perfect mirror image in a flat, two-dimensional realm governed solely by quantum mechanics, a conformal field theory, or CFT. No gravity, no curvature, just particles dancing to the rules of quantum physics. The two descriptions, though seemingly unrelated, are mathematically identical. It's as if the entire 3D universe is a holographic projection, and the real source code is hidden on its 2D boundary. This duality isn't just a clever metaphor, it's a groundbreaking tool for physicists. Take a black hole in the 3D AD/S universe. Calculating its behavior is a nightmare, tangled in the complexities of general relativity. But through the looking glass of AD/CFT, that same black hole corresponds to a seething, ultra-hot plasma on the 2D boundary. Suddenly, the problem becomes tractable. The plasma's quantum interactions, though unfolding in fewer dimensions, encode all the information about the black hole's gravity, its thermodynamics, even its mysterious entropy. It's like swapping a Rubik's Cube for a sheet of paper with the solution written out, same puzzle, simpler form. What makes this so revolutionary is how it bridges the chasm between quantum mechanics and general relativity, two theories that have stubbornly refused to reconcile for over a century. Quantum mechanics rules the tiny realm of particles where probabilities flicker and particles teleport through barriers. General relativity governs the cosmos, where gravity sculpts galaxies and warps time. Put them together and the math explodes into infinities, but AD/CFT offers a lifeline. Gravity in 3D might not be fundamental at all. Instead, it could emerge from quantum interactions on a 2D surface, like a mirage shimmering above desert sands. Consider a thought experiment. You're playing a video game with hyper-realistic graphics, forests rustle, rivers flow, shadows stretch with the sun. Now imagine pausing the game and digging into its code. You'd find not trees or water, but lines of instructions, algorithms dictating how pixels behave. AD/CFT suggests reality might work similarly. The 3D universe we perceive, the stars, the planets, even our own bodies, could be the graphics rendered by a deeper, flatter layer of quantum code. The catch: this code doesn't live inside our universe. It's written on the edge like a cosmic firewall, encoding everything within. The implications ripple far beyond black holes. AD/CFT has become a Rosetta Stone for theoretical physics, cracking problems in nuclear physics, superconductivity, even the birth of spacetime itself. In labs, scientists simulate the 2D quantum systems predicted by this duality, uncovering hints about how space might emerge from entanglement, a quantum phenomenon where particles remain mysteriously linked across distances. Some even speculate that our own universe, though not perfectly described by anti-de Sitter space, might still be holographic at its core. Yet the most mind-bending twist is this: if AD/CFT holds, then the very fabric of space isn't a static backdrop. It's dynamic, woven from quantum connections, as if the emptiness between stars is a tapestry of invisible threads. Gravity, the force that shapes the cosmos, might not be a fundamental force at all, just a side effect of how information is organized on some distant, flat horizon. That means the chair beneath you, the ground under your feet, the vast expanse of the night sky, all of it could be a grand illusion, a 3D shadow cast by quantum whispers on the edge of reality. And if that doesn't make you question the nature of existence, just wait. The rabbit hole goes deeper. Quantum entanglement, Einstein's infamous, spooky action at a distance, might hold the key to understanding how a flat, two-dimensional boundary could conjure our three-dimensional universe. Picture two entangled particles separated by vast cosmic distances, yet mysteriously linked. Change one, and the other instantly responds as if space between them doesn't exist. Now, imagine this eerie connection isn't just a quirk of quantum mechanics, but the very stitching that sews spacetime together. That's the bold claim made by the ER=EPR conjecture, a theory suggesting that entangled particles are connected by tiny, invisible wormholes, bridges through spacetime so short they render distance meaningless. If true, it means every quantum handshake might be a microscopic thread weaving the holographic illusion we call reality. Think of spacetime as a vast, shimmering tapestry. Each thread represents an entangled pair of particles, and the tighter the entanglement, the stronger the thread. Pull one thread, and the whole fabric adjusts, not because something is magically teleporting, but because the fabric itself is built from these connections. Now zoom out to the holographic principle's two-dimensional boundary. What if every entangled pair on that flat surface is like a pixel in a cosmic display, projecting the depth and structure of our 3D world? The more entangled the pixels, the richer the illusion of space. It's as if the universe is a 3D shadow cast by quantum whispers on a distant 2D screen, with entanglement acting as the projector's hidden wiring. Experiments are already hinting at this mind-bending possibility. In labs, physicists manipulate entangled particles to probe how information spreads, and the results look suspiciously like spacetime itself is emerging from their quantum links. For instance, throw a pebble into a pond and ripples spread in predictable circles, but in a quantum pond, the ripples don't just travel. They appear everywhere at once, as if the water's surface is secretly folded into higher dimensions. This bizarre behavior mirrors how entangled particles defy classical geometry, suggesting that spacetime might not be a fixed stage, but a dynamic network of quantum relationships. The implications are staggering. If spacetime emerges from entanglement, then black holes, those cosmic shredders of reality, might just be knots of ultra-entangled information. Even the Big Bang could be reinterpreted as a quantum reset, where entanglement patterns rewrote the rules of dimensionality itself. It's a vision that blurs the line between physics and philosophy, where the universe isn't a place, but a process, a ceaseless computation unfolding on a hidden 2D canvas. And if that's true, the next time you feel the solidity of the ground beneath you, remember, you might just be standing on a hologram held together by ghostly quantum threads we're only beginning to unravel. If you zoomed in on the fabric of reality, way beyond atoms, beyond quarks, down to the smallest possible scale, you might find something startling. Picture the universe as a vast cosmic screen, not smooth and continuous, but buzzing with tiny, discrete pixels. Not pixels of light, but pixels of information, each one a fundamental unit of spacetime itself. This is the Planck scale, where distances shrink to a billionth of a trillionth of the width of an atom. And here, the holographic principle suggests reality might not be fluid at all. Instead, it could be digital, a shimmering mosaic of data points etched onto a hidden two-dimensional surface. Think of a high-definition TV screen. From a distance, the image looks seamless, faces glow, landscapes roll, colors blend. But get close enough and you'll see the individual pixels, the building blocks of the illusion. Now imagine the universe works the same way. The chair you're sitting on, the stars overhead, even the flow of time, all of it might emerge from countless Planck-sized pixels on a distant 2D boundary. Each pixel wouldn't just store color or brightness, but the very essence of existence, the position of particles, the curvature of spacetime, the quantum states that define reality. It's as if the universe is a cosmic jigsaw puzzle, and the pieces aren't material, they're pure information. This raises a dizzying question. If reality is pixelated, what happens when you reach the smallest possible resolution? Just as a digital photo breaks apart when you zoom in too far, could the universe reveal its scaffolding if we looked closely enough? Some theories suggest that at the Planck scale, spacetime itself might become grainy, like sand slipping through fingers. Particles wouldn't move smoothly, but in tiny, imperceptible jumps like frames in a stop-motion film. Even time might tick forward in discrete steps, not as a river but as a flickering series of moments. The unsettling implication: our perception of a continuous, flowing reality could be a trick of the scales we're used to, a cosmic sleight of hand. The holographic principle takes this further. If the universe is a projection from a 2D surface, then what we perceive as depth, volume, and even causality might just be clever data compression. Consider a black and white movie. The film strip is flat, but when projected, it creates the illusion of three-dimensional drama, light and shadow fooling the brain into seeing depth where none exists. Similarly, the holographic universe could be a grand cinematic trick, with the real film existing on a flat plane we'll never see. The cosmos wouldn't be a thing so much as a process, a dynamic computation unfolding on a hidden surface. What does this mean for the limits of perception? Just as a fish might never grasp the concept of air, we could be fundamentally blind to the true nature of reality. Our brains evolved to navigate a world of medium-sized objects moving at medium speeds, not to perceive Planck-scale pixels or hidden dimensions. It's like trying to read a novel by pressing your face against the page. The letters blur and the story vanishes. Yet, if the holographic principle is correct, there might be glitches in the matrix, subtle anomalies where the universe's code shows through. Some physicists hunt for these irregularities in the cosmic microwave background, the afterglow of the Big Bang, searching for telltale patterns that betray the pixelation beneath. The implications ripple outward. If reality is information at its core, then the laws of physics might not be etched in stone, but more like algorithms' rules that can, in theory, be rewritten. It challenges the very notion of objectivity. What we call real might just be a user interface, a rendering of deeper data for beings like us. The solidity of the world, the certainty of time's arrow, even the distinction between past and future, all could be emergent properties, illusions woven by the hologram. And if that's true, the next question isn't just how the universe works, but who or what is running the simulation. Scientists are hunting for cracks in reality, tiny glitches that might reveal whether we're living inside a cosmic hologram. One of the most daring experiments involves a device called a holographic interferometer. Picture this: a laser beam split in two, traveling down perpendicular paths before recombining. In a perfectly smooth universe, the beams realign seamlessly. But if space-time is pixelated at the Planck scale, like a digital image up close, those beams might stutter, their wavelengths jittering as they brush against the grain of reality itself. This holographic noise would be faint, a whisper buried under cosmic static. But if detected, it could be the first hard evidence that our three-dimensional world is a projection from a deeper, flatter layer of information. Teams like the Fermilab Holometer have spent years chasing this ghostly signal. Their machine, essentially an ultra-precise ruler for spacetime, listens for microscopic trembles in the fabric of reality, fluctuations so small they'd make an atom look like a mountain. The results so far inconclusive. The noise they've detected could be quantum jitters, instrumental error, or something even stranger. But the hunt continues, with next-generation interferometers designed to peer even closer at the Planck scale, where the universe's pixels might finally come into focus. Meanwhile, astronomers scrutinize the oldest light in existence, the cosmic microwave background, or CMB, for anomalies that might betray the universe's holographic origins. This afterglow of the Big Bang stretches across the sky like a fossilized fingerprint, and hidden in its faint ripples could be clues. Some researchers claim to have spotted odd, large-scale asymmetries patterns that don't fit standard cosmic models. Could these be artifacts of a pixelated universe, like digital artifacts in a compressed image? Others argue the data is too noisy, the signals too ambiguous. After all, the CMB is a palimpsest layered with interference from galaxies, dust, and the cosmic web. Teasing out holographic signatures from that chaos is like listening for a single wrong note in a symphony played across 14 billion light-years. The speculative nature of these searches hasn't dampened their audacity. Some theorists propose even wilder tests, like probing the behavior of entangled particles near black holes, where gravity's grip might stretch quantum links to their limits, revealing the stitches in spacetime's holographic fabric. Others suggest that if the universe is a projection, its resolution might have limits, causing high-energy particles to behave differently at extreme scales, like pixels breaking apart in a zoomed-in video game. Yet for all the ingenuity, the holographic principle remains tantalizingly out of reach. Negative results don't disprove it, they just mean we haven't looked hard enough or in the right way. The universe guards its secrets closely, and the tools we have might be too crude to read its deepest code. But the mere possibility has reshaped how we think about reality. Whether through interferometers trembling at quantum scales or telescopes passing ancient light, the message is clear. If the universe is a hologram, it's the most convincing illusion ever crafted. And the truth, if it's out there, will take more than a magnifying glass to uncover. It'll demand rewriting the rules of how we observe, measure, and even conceive existence itself. If reality is nothing more than a holographic projection, an intricate illusion woven from information encoded on some distant two-dimensional surface, what does that say about you? Your thoughts, your choices, the vivid tapestry of your inner life. The holographic principle doesn't just challenge our understanding of space and time. It unravels some of philosophy's oldest and most persistent questions. Free will, for instance, takes on a surreal new light. If every decision you've ever made, every twist of fate you've experienced, is just data unfolding on a cosmic hard drive, does choice even exist? Or are we all, from the smallest atom to the grandest galaxy, merely reading lines from a script written in some unfathomable quantum code? This isn't just speculation. Philosophers and physicists alike have wrestled with these implications. Some argue that if the universe is holographic, free will might be an emergent property, like the illusion of depth in a 3D movie. The pixels on the screen don't choose how to arrange themselves, but the story they create feels dynamic, alive. Others counter that determinism could be absolute, a universe where every event, from the birth of stars to the flicker of a neuron, is predetermined by the underlying 2D data. It's a modern twist on an ancient debate. Are we actors or just characters in a story we didn't write? Then there's consciousness itself. If reality is a projection, what's projecting us? Our sense of self, the I behind your eyes, feels undeniable, immediate. But if the brain is just part of the hologram, processing information like a biological quantum computer, does that make consciousness an illusion too? Idealism, a school of thought dating back to Plato, suggests something eerily similar, that the material world is secondary, a shadow cast by deeper mental or spiritual truths. The holographic principle, in a way, flips idealism on its head. Instead of mind creating matter, it's information creating both. The universe isn't just in your head is in the universe's code. Simulation theory, popularized by thinkers like Nick Bostrom, adds another layer to the puzzle. If advanced civilizations could one day run hyper-realistic simulations of entire worlds, how would we know we're not inside one? The holographic principle doesn't require a sim creator. It suggests reality might intrinsically be a kind of computation, but the parallels are striking. Both ideas force us to confront the same unsettling question. What if the realness of our experiences is just a side effect of something far more abstract? Digging deeper, the holographic principle blurs the line between perception and reality in ways that would make Descartes dizzy. If the chair you're sitting on is just a projection, does that make it less real? Buddhists might say no, that all phenomena are empty of inherent existence, interdependent illusions. Quantum physicists, in their own language, might agree. Particles only gain definite properties when observed, as if the universe is waiting for someone to render it. The holographic principle doesn't dismiss our experiences, it recontextualizes them. The warmth of sunlight, the taste of fruit, the ache of loss, they're no less meaningful because they're woven from information. If anything, it makes them more astonishing. This raises one final profound irony. Science, often seen as the ultimate debunker of mysteries, might have led us right back to the oldest questions of all. The holographic principle doesn't diminish reality. It reveals how much more bizarre and beautiful it might be than we ever dreamed. Whether you call it a projection, a simulation, or an illusion, one thing's certain: the universe is far stranger than it seems. And the closer we look, the more it asks us to reconsider not just how the world works, but what it is and what we are within it. Long before holograms or quantum physics entered the picture, humanity grappled with the idea that reality might not be what it seems. Take Plato's famous allegory of the cave, written over 2,000 years ago. He described prisoners chained in a dark cavern, mistaking shadows dancing on the wall for the entirety of existence. When one prisoner escapes and sees the sunlit world outside, he realizes the shadows were mere projections, an illusion masking a deeper, truer reality. Sound familiar? It's a striking precursor to the holographic principle, where our three-dimensional world might be nothing more than a flickering show cast from a hidden, more fundamental layer. Eastern philosophies arrived at similar conclusions even earlier. The ancient Hindu concept of Maya teaches that the material world is an illusion, a veil obscuring the ultimate nature of reality. Buddhist traditions echo this, describing existence as a dream or a reflection, real in one sense, yet fundamentally ephemeral. What's remarkable is how these ideas, born from meditation and introspection, align with the radical edges of modern physics. The holographic principle doesn't just suggest the universe is a projection. It gives that projection a mathematical framework, a way to quantify what mystics and philosophers intuited millennia ago. The parallels don't stop there. In the 17th century, philosopher René Descartes famously doubted everything he could, questioning whether an evil demon might be deceiving his senses. Today, that demon might as well be a cosmic algorithm, a master program rendering our perceptions from a lower dimensional blueprint. Even early science fiction writers like Edwin Abbott, in his 1884 novella Flatland, toyed with dimensional illusions, imagining two-dimensional beings oblivious to the third dimension towering above them. Abbott's flat squares and circles would find kinship with modern theories where depth and volume emerge from flat information. Perhaps the most uncanny historical thread is alchemy. While often dismissed as proto-chemistry, alchemists sought to transmute base metals into gold, a metaphor for transforming perception into enlightenment. Their quest mirrors modern physics' search for the code beneath reality, the rules that might let us rewrite the universe's operating system. Both pursuits, separated by centuries, share a common driver: the suspicion that the world is malleable, that its solidity is a trick waiting to be decoded. What does this pattern tell us? That the holographic principle isn't just a scientific breakthrough, it's the latest chapter in an age-old dialogue about the nature of existence. Whether through parable, philosophy, or particle physics, humans keep circling the same profound question: is reality real, or is it a construct, a story we're all tangled inside? The answers vary, but the hunger to ask never fades. And if history's any guide, the next revelation might make today's holographic universe seem as quaint as shadows on a cave wall. Not everyone is convinced the universe is a holographic projection. Skeptics argue that without direct experimental proof, the holographic principle remains more metaphysics than physics, a captivating idea, but one still floating in the realm of mathematical speculation. After all, how do you test something that suggests reality itself is an illusion? The biggest hurdle is that our universe doesn't perfectly match the anti-de Sitter space described by AD/CFT correspondence, the mathematical backbone of the holographic principle. AD/S space is a theoretical playground with negative curvature, like an infinite cosmic saddle, while our actual universe appears flat or slightly positively curved. Critics point out that stretching a model built for one geometry to fit another is like using a subway map to navigate a forest. It might hint at patterns, but the terrain's all wrong. Enter loop quantum gravity, one of the holographic principle's fiercest rivals. Instead of reducing reality to a 2D surface, this framework proposes that spacetime is woven from tiny, indivisible loops, a fabric of interwoven threads vibrating at the smallest scales. Think of it as a cosmic mesh where each knot represents a quantum of space. Unlike the holographic principle's focus on information encoding, loop quantum gravity keeps dimensionality intact, treating space and time as fundamental rather than emergent. It's a clash of philosophies. One theory dissolves the universe into data on a distant screen, while the other builds it stitch by stitch from tangible quantum threads. Then there's the elephant in the room: testability. The holographic principle's most tantalizing predictions, like Planck-scale pixelation or holographic noise, hover at energies trillions of times beyond what our best particle colliders can reach. Detecting these effects would require instruments of unimaginable precision, leaving some physicists to wonder if the theory is even falsifiable. Without empirical anchors, does it risk becoming a modern-day epicycle, an elegant mathematical story with no connection to reality? Yet defenders counter that dismissing the holographic principle for its current untestability ignores history. Black holes were once considered mathematical oddities until telescopes proved them shockingly real. The Higgs boson took half a century to detect, gravitational waves a century. Science often races ahead of technology, with theory lighting the path for future experiments. Holographic noise might remain elusive now, but as interferometers grow more sensitive and quantum computers more powerful, we might yet glimpse the universe's underlying code. The debate also hinges on AD/CFT's flexibility. While our universe isn't pure AD/S, recent work suggests the correspondence might adapt to more general settings, like a recipe tweaked for different kitchens. Some researchers are exploring DS/CFT, a variant where the holographic boundary describes a de Sitter universe, one like ours, expanding at an accelerating pace. Others probe how holography might emerge from quantum error-correcting codes, the same math that keeps your smartphone from glitching. These twists don't prove the principle, but they show it's evolving beyond its original, rigid formulation. What's striking is how the controversy mirrors deeper divides in physics. Is spacetime fundamental or emergent? Is gravity primary or a side effect? The holographic principle's boldest claim, that dimensionality itself is an illusion, pushes against centuries of intuition. Yet that's often where breakthroughs hide, in the cracks between what we know and what we dare to imagine. Whether the universe is a hologram, a quantum net, or something stranger still, the questions themselves are reshaping how we see reality seems. And in that tension between skepticism and possibility, science finds its most fertile ground. Time feels like the most undeniable part of existence, the steady tick of a clock, the aging of stars, the march of history. But what if time itself is just another layer of the cosmic illusion? The holographic principle doesn't just challenge our understanding of space, it turns time inside out, suggesting it might not be a fundamental feature of reality, but something that emerges from the interplay of information on that hidden 2D surface. Take the Wheeler-DeWitt equation, one of the most radical equations in physics. It describes the entire universe as a timeless, frozen block, a single mathematical object where past, present, and future exist simultaneously. No ticking clock, no arrow of time, just static relationships between quantum states. At first glance, this seems absurd. How could a universe with no time give rise to our vivid experience of moments flowing into one another? But think of a movie reel. Each frame exists all at once, unchanging, until the projector spins them into motion. The holographic principle suggests time might work the same way, a dynamic illusion rising from a timeless code. This taps into a deeper idea called emergent time, where change isn't built into the universe's foundation but arises from how quantum information interacts. Imagine a chessboard where the pieces rearrange themselves in perfectly predictable patterns. If you only saw snapshots of the board, you'd infer a sequence, a before and after. But the rules governing the pieces don't reference time at all. They're just abstract relationships. Similarly, the 2D boundary of the holographic universe might encode relationships between quantum states that, when projected into 3D, create the sensation of time passing. Here's where it gets even stranger. Some versions of the holographic principle suggest that what we perceive as time could be a kind of cosmic scale entanglement. Just as entangled particles influence each other instantaneously, the quantum links on the 2D boundary might weave a fabric that, when viewed from within, appears as causality, one event leading to another. It's like watching a crowd do the wave in a stadium. From afar, you see a ripple moving through space, but no single person is the wave. The motion emerges from countless individual actions. In the holographic universe, time might be the wave, and we're just the spectators caught in its sweep. Visualizing this is tricky, but picture a flipbook lying flat on a table. Each page is static, unchanging, yet when you flip through them, the images seem to move. Now, imagine those pages are quantum states on the 2D boundary, and the flipping is the universe computing its own evolution. From inside the flipbook, creatures like us would experience time as the progression of frames, but from outside, it's all just data sitting there at once. Critics argue this reduces time to a psychological trick, a byproduct of how our brains process information. But supporters counter that emergent time doesn't make our experience any less real. It just explains why time feels the way it does. After all, temperature isn't a fundamental property either. It emerges from the jostling of molecules, yet no one would say a scorching summer day is an illusion. Similarly, time might be a side effect of deeper physics, a story the universe tells itself to make sense of quantum relationships. The implications ripple through everything from black holes to the Big Bang. If time isn't fundamental, then the beginning of the universe might not be a singular moment but a computational threshold, the point where the holographic code starts rendering change. Even entropy, the force that gives time its arrow, could be reinterpreted as information spreading across the boundary, like ink dispersing in water. So the next time you check your watch, consider this. The seconds ticking away might not be marking some universal clock, but the unfurling of a cosmic algorithm, one where time is the output, not the input. And if that's true, then past, present, and future might not be what we think they are. They could be pixels in a much bigger picture, one we're only beginning to decode. Claude Shannon, the father of information theory, once reduced the entire universe to a single, audacious question. What if everything, every star, every thought, every heartbeat is just information in disguise? In the 1940s, Shannon wasn't thinking about holograms or black holes. He was trying to solve a practical problem: how to send messages without losing data to noise. But his equations revealed something far bigger. Information, he showed, isn't just words or numbers, it's the fundamental currency of reality, measurable in bits, the binary yes or no choices that underpin everything from DNA to computer code. Fast forward to today, and Shannon's ideas have collided with the holographic principle in a way that redefines existence itself. If reality is built from information, then the universe might not just contain data, it might be data, a cosmic computation unfolding from a hidden 2D source. This isn't just poetic speculation. Enter the Bekenstein bound, a theoretical limit discovered by physicist Jacob Bekenstein in the 1980s. It states that any region of space, no matter how large, can only hold a finite amount of information, and that limit depends not on volume but on surface area. Picture a sphere. Classically, you'd assume its storage capacity grows with its size, more space, more room for data. But the Bekenstein bound says no. The maximum information it can contain is proportional to the area of its boundary, not its volume. It's as if a hard drive's storage didn't scale with its thickness, but only with the circumference of its casing. This bizarre rule mirrors how holograms work, where a 3D image is encoded on a 2D surface. The math suggests that our universe, with all its apparent depth, might be similarly constrained, a sprawling illusion projected from a flatter, denser plane of information. To grasp why this is revolutionary, think about compression. A high-resolution photo might take up megabytes, but if you find the right algorithm, you can shrink it dramatically without losing essential detail. The holographic principle hints that the universe does this naturally, compressing 3D physics into 2D data with perfect efficiency. Black holes are the ultimate test case. When matter falls into one, it doesn't just vanish. It leaves an imprint on the event horizon, like ink on a cosmic ledger. The Bekenstein bound ensures that even the most chaotic black hole's interior can be fully described by the information scribbled on its surface. The same logic might apply to the cosmos. All the galaxies, planets, and particles we see could be a kind of cosmic zip file, unpacked into 3 dimensions by the laws of physics. Shannon's work adds another layer. He showed that information is immune to destruction. It can change form but never disappear. This aligns perfectly with the holographic view, where information falling into a black hole isn't lost but smeared across its horizon. It's like burning a book. The pages vanish, but if you could somehow capture every wisp of smoke and ash, the text could theoretically be reconstructed. In the holographic universe, reality might be that reconstruction, a dynamic recreation of data from its conserved, lower-dimensional blueprint. The implications are staggering. If information is the true bedrock of existence, then matter, energy, even the passage of time might just be how that data feels when processed by beings like us. A pixel on a screen isn't red in itself. It's a voltage interpreted by software and rendered by hardware. Similarly, an electron might not be a tiny ball, but a knot of information resolved by the universe's operating system. This flips the script on materialism. The chair you're sitting on isn't solid because of atoms, but because of the quantum bits encoding its properties on some distant, flat frontier. Critics point out gaps. The Bekenstein bound strictly applies to add S-space, a theoretical playground with negative curvature, not our flatter cosmos. And while information theory beautifully describes how data moves, it's silent on why the universe bothers computing itself at all. But these mysteries don't weaken the connection, they highlight how deep it goes. From Shannon's noisy telephones to black hole thermodynamics to the pixels of spacetime, the thread is unmistakable. Reality might not be a canvas, but the painting itself, an artwork drawn in data on the edge of everything we know. And if that's true, the next question isn't just about physics, it's about what or who is holding the brush. If the universe is a holographic projection, where does consciousness fit into the equation? In quantum mechanics, particles exist in a haze of possibilities until an observer measures them, a phenomenon called wave function collapse. Some interpretations suggest the act of observation itself plays a role in shaping reality. Now stretch that idea to the holographic principle. If our three-dimensional world is a projection from a two-dimensional boundary, could consciousness be the mechanism that renders the illusion into something tangible? It's a provocative thought that the mind doesn't just perceive reality but might participate in its creation, like a cosmic feedback loop between observer and observed. This isn't just philosophical musing. Certain strands of theoretical physics flirt with the idea that information processing, the sort that might underpin consciousness, could be fundamental to how the universe functions. Take physicist John Wheeler's participatory universe hypothesis, which posits that observers are necessary to bring the cosmos into definite existence. In a holographic framework, this could mean that conscious entities aren't passive bystanders but active decoders, translating the 2D boundaries data into the rich, textured world we experience. Think of it like a VR headset. The software generates the environment, but it's the user's interaction that gives it meaning and form. But here's where caution is essential. While the parallels are tantalizing, leaping to conclusions risks veering into pseudoscience. There's no empirical evidence yet that consciousness directly influences the holographic projection. The universe hummed along for billions of years before life arose after all. Skeptics argue that anthropocentric theories like these mistake correlation for causation, projecting human experience onto impersonal physics. The holographic principle, in its strictest form, is about information encoding, not mind over matter mysticism. That said, the intersection of consciousness and holography isn't purely speculative. Researchers like neuroscientist Carl Pribram once proposed that the brain itself might process information holographically, with memories and perceptions distributed across neural networks, much like data smeared on a 2D surface. While his model isn't mainstream today, it hints at a deeper symmetry. If the universe is holographic and the brain operates in a similar fashion, could there be a resonance between the two? A universe built on information might naturally give rise to systems like minds capable of interpreting it. The debate often circles back to a humbling truth. We don't yet know what consciousness is, let alone how it might interact with spacetime's fundamental structure. Is it an emergent property of complex systems, as materialists argue, or something more intrinsic, woven into the fabric of reality itself? The holographic principle doesn't answer these questions, but it reframes them in a startling new light. If reality is a kind of computation, then consciousness might be the universe's way of observing itself, a fleeting glitch in the code that allows the hologram to ask, "What am I?" Until experiments can bridge the gap between quantum observation, information theory, and subjective experience, these ideas remain at the edge of science. But that's where the most fascinating questions often lie, not in what we know, but in what we're just beginning to imagine. Whether consciousness shapes the hologram or simply arises from it, one thing's certain: in a universe this strange, the observer might be the greatest mystery of all. The holographic universe isn't just a playground for physicists, it's been a goldmine for storytellers, popping up everywhere from blockbuster movies to chart-topping music videos. Take The Matrix, the sci-fi classic that turned reality into a digital illusion. When Neo wakes up in that gooey pod, realizing his entire life was a simulation, it wasn't just cool visuals, it was a Hollywood spin on the same questions physicists ask today. What if our world is just data? What if the body you're in isn't yours, but a rendered avatar in a grander game? The film's red pill moment mirrors the shock of the holographic principle. The universe might not be what it seems, and uncovering the truth could rewrite everything. Then there's Westworld, where android hosts grapple with the nature of their existence, their memories rewritten like lines of code. The show's central twist that the park's maze isn't a physical place but a journey to self-awareness echoes the holographic idea that reality might be a construct, a narrative woven from underlying data. Even the host's repeated loops of suffering mirror how, in a holographic universe, entropy and time might just be patterns in a deeper computation. These stories resonate because they tap into the same unease that keeps physicists up at night. If reality is a projection, who's holding the projector? Music jumps on the bandwagon too. Remember Tupac's ghostly performance at Coachella in 2012? A hologram of the late rapper took the stage, thrilling crowds with its uncanny realism. More recently, digital avatars of ABBA and K-pop stars have performed as holograms, blending the line between presence and illusion. These spectacles don't just entertain, they make the holographic principle visceral. When fans scream for a long-dead artist reborn as light and pixels, it's a cultural rehearsal for the day we might question whether we're just as ephemeral, flickering into existence from some cosmic hard drive. But pop culture doesn't always get the science right. Star Trek's holodecks, for instance, treat holograms as solid, touchable objects, a far cry from the abstract data surfaces of theoretical physics. And while Black Mirror episodes like USS Callister explore digital consciousness, they often skip the messy math of emergent spacetime. These creative liberties matter because they shape how audiences imagine holography. For every person who Googles add S/CFT after watching The Matrix, there's another who walks away thinking holograms are just fancy VR. Yet the missteps are as revealing as the accuracies. Art thrives on metaphor, distilling complex ideas into emotional truths. When Westworld's hosts discover their lives are scripts, it's not a physics lesson, it's a gut punch about free will. When Tupac's hologram beams onto stage, it's not about quantum entanglement, it's about longing, legacy, and the hunger to defy time. These stories work because they take the holographic principle's chilliest implications, that we might be shadows on a wall, and warm them with human stakes. That's the secret sauce. Physics gives us equations, art gives us shivers down the spine. The holographic principle captivates because it straddles both, offering a lens to question not just how the universe works, but what it means to be real. Whether through a philosopher's dilemma or a pop star's pixelated encore, one thing's clear: we're obsessed with the idea that reality might be thinner than it seems. And if the holographic theorists are right, our obsession might just be part of the code. When you picture a hologram, chances are you're thinking of Princess Leia's plea for help in Star Wars, a shimmering, translucent figure suspended in midair, speaking as if she were really there. Or maybe it's the holographic security stripe on your credit card, shifting colors as you tilt it under the light. These are literal holograms, carefully engineered illusions that use light interference patterns to trick our eyes into seeing depth where none exists. They're real, tangible technologies, and they work by encoding 3D information onto a 2D surface, like a film or a screen, then reconstructing that information when light hits it just right. But here's the catch: the holographic principle in physics isn't about glowing blue projections or fancy security features. It's something far stranger, a radical reimagining of how reality itself might be structured. Let's break it down side by side. A technological hologram, like Leia's projection, starts with a laser beam split in two. One beam bounces off the object you want to holograph, say, a tiny model of the Death Star, while the other serves as a reference. When these beams recombine on a photographic plate, their interference pattern creates a kind of frozen light blueprint. Shine another laser through that plate later, and voila, a 3D image pops out, floating eerily in space. But here's the key: the image isn't actually three-dimensional. It's a flat surface manipulating light to appear deep, like a magician's sleight of hand. Now take that idea and scale it up to the entire universe. The holographic principle suggests that all the matter, energy, and even space-time we experience might be analogous to that floating Death Star, an elaborate projection from a hidden 2D surface we can't see or touch. But unlike Princess Leia's hologram, there's no laser, no photographic plate, no deliberate engineering. Instead, the projection happens naturally, woven into the fabric of physics itself. The three-dimensional world we perceive the weight of a coffee cup, the curve of a planet's orbit, the heat of a summer breeze, could be emergent, rising from quantum interactions on a distant boundary like shadows cast by a fire. The biggest difference, literal holograms are optical illusions. They play tricks on our eyes. Cosmic holography, if true, would mean the universe is an ontological illusion, a trick played on reality itself. With a credit card hologram, you can scratch the surface and feel the flat film beneath. But if the universe is holographic, there's no scratching through to the 2D layer. It's not a physical object tucked away somewhere. It's a fundamental feature of how information organizes space-time. Think of it like this. Watching a 3D movie with glasses is a passive experience. The screen doesn't change based on where you sit. But in a holographic universe, the screen, that hypothetical 2D boundary, isn't just projecting a static image. It's dynamically encoding every interaction, every collision of particles, every thought in your brain in real time. The projection isn't pre-recorded. It's a live computation, a cosmic rendering engine updating itself moment by moment. This distinction matters because it keeps us from oversimplifying the physics. Calling the universe a hologram can make it sound like we're living in a high-tech simulation run by some advanced civilization. But the holographic principle isn't about creators or programmers, it's about the inherent structure of reality. The universe isn't like a hologram. It is holographic in a deep mathematical sense, with dimensionality emerging from quantum entanglement and information density in ways we're still struggling to understand. So next time you see a holographic sticker or a sci-fi hologram, remember, the real magic isn't in the glowing light show. It's in the possibility that every atom in your body, every star in the sky, might be part of a far grander illusion, one written not in lasers, but in the hidden language of spacetime's own code. There's a quiet elegance to the math behind the holographic principle, a kind of symmetry so profound it feels like peering into the universe's hidden blueprint. Take the Maldaisner duality, named after physicist Juan Maldaisner, who unveiled it in 1997. At its core, this mathematical framework bridges two seemingly unrelated worlds, a five-dimensional space riddled with gravity, and a four-dimensional quantum field theory humming along without gravity at all. The equations don't just line up, they mirror each other like a perfect dance between dimensions. What's breathtaking isn't just that it works, it's how it works. The math reveals that the chaotic swirl of particles in the four-dimensional world encodes with perfect fidelity the warped geometry of the five-dimensional one. It's as if the universe left a Rosetta Stone buried in its own equations, whispering that gravity and quantum physics aren't rivals, they're two dialects of the same cosmic language. This symmetry isn't accidental. Throughout history, the most revolutionary leaps in physics have sprung from moments where math's beauty hinted at nature's truths. Einstein's general relativity, for instance, emerged from the elegance of tensor calculus, transforming gravity from a mysterious force into the curvature of spacetime itself. The Maldaisner duality carries that same torch. Its equations are sparse, almost minimalist, yet they bind together theories that once seemed irreconcilable. Imagine trying to describe a sphere using only flat, square tiles at first. It seems impossible. But with enough tiles arranged just right, the curvature emerges. The holographic principle suggests that our 3D universe might be that emergent sphere, and the 2D boundary is the tile floor whispering the pattern. What's striking is how the math sidesteps intuition. We're wired to think in terms of cause and effect, of objects moving through space. Yet the Maldaisner duality treats spacetime like a secondary character, a shadow cast by quantum interactions on the boundary. It's like discovering that the plot of War and Peace is secretly embedded in the barcodes on its cover. The story's richness isn't lost, it's just stored differently, in a form that's leaner but no less complete. This isn't just clever accounting, it's a clue that the universe might prioritize information over substance, relationships over rigid structures. The implications ripple beyond black holes and string theory. This kind of mathematical harmony often signals a deeper truth, like a tuning fork vibrating at reality's fundamental frequency. When Paul Dirac derived antimatter from an equation's symmetrical roots, or when Emmy Noether proved that every symmetry in physics corresponds to a conservation law, they weren't just solving puzzles, they were uncovering the grammar of existence. The holographic principle's math hints at a similar grammar, one where dimensionality is fluid and the universe's vastness is an artifact of how we read the code. For those who speak math, this is where the magic happens. The equations aren't just tools, they're portals. A single line of symbols can collapse centuries of debate or reveal hidden doors in what we thought was a solid wall. And if the holographic principle holds, those doors might lead us somewhere unimaginable, to a universe where the deepest truths aren't written in the stars, but in the silent, shimmering language of quantum bits on the edge of everything. The holographic principle isn't the only radical idea tearing at the edges of reality. Imagine walking into a cosmic library where every shelf holds a different theory of existence, each one more mind-bending than the last. Simulation theory, for instance, argues we're living in an advanced civilization's computer program, with every quark and supernova rendered in flawless detail. Unlike holography, which roots reality in natural physics, a 2D boundary encoding 3D phenomena, simulation theory leans on artificial creators. It's the difference between discovering the universe is a mathematical poem and suspecting it's an alien screensaver. Both challenge objectivity, but where holography emerges from black hole physics, simulation theory springs from Silicon Valley's obsession with virtual worlds. Then there's the multiverse, a sprawling ensemble of parallel universes bubbling up from eternal inflation or quantum branching. While holography flattens reality into a surface, the multiverse explodes it outward, suggesting every decision spawns a new timeline. Picture a hall of mirrors where each reflection is a fully realized cosmos, some with laws of physics so alien they'd make our universe look like a quaint anomaly. Holography and the multiverse both imply reality is vaster than we perceive, but their mechanisms clash. One condenses the cosmos into data, the other endlessly multiplies it. Brain-world scenarios born from string theory offer another twist. Here, our 3D universe might be a membrane, or brain, floating in a higher dimensional space, occasionally colliding with others like sheets in a cosmic dryer. These collisions could explain events like the Big Bang. Unlike holography's data on a surface model, brain worlds retain traditional dimensionality but embed it in unseen realms. It's as if holography shrinks the stage while brain worlds expand the theater. Even quantum mechanics serves up its own existential curveball, cubism, which treats reality as a kaleidoscope of personal probabilities. In this view, the universe isn't just encoded, it's subjective, reshaped by every observation. Compare that to holography's objective, if illusory, 3D projection. Both reject classical materialism, but where holography is a cosmic blueprint, cubism is a choose-your-own adventure book written in quantum ink. So where does holography stand in this menagerie of metaphysical alternatives? It's uniquely poised between the concrete and the speculative. Unlike simulation theory, it doesn't require programmers. Unlike the multiverse, it doesn't inflate reality but compresses it. And unlike brain worlds, it doesn't rely on hidden dimensions, it erases them. What unites these theories is their audacity. All suggest reality is a thin veil over something far stranger. The holographic principle just happens to have the sharpest math and the boldest claim that the veil isn't even three-dimensional. In this carnival of cosmic ideas, holography isn't just another ride. It's the hall of mirrors that makes you question whether the exit was ever real to begin with. The search for proof of a holographic universe is far from over. In fact, the most ambitious experiments are just getting started. Picture a machine so sensitive it could detect the faintest tremors in spacetime itself, vibrations hinting at the universe's pixelated underpinnings. Next-generation quantum gravity detectors, like the proposed space-based observatory LISA, aim to do exactly that by measuring ripples in spacetime with lasers spanning millions of kilometers. These instruments could uncover anomalies, tiny fluctuations where gravity behaves oddly at microscopic scales. Such glitches might betray the hidden 2D code, like static on a radio revealing a scrambled signal beneath. Meanwhile, astronomers are turning their telescopes toward the cosmic microwave background with unprecedented precision. The CMB is more than ancient light. It's a fossilized imprint of the universe's infancy, and buried in its subtle patterns could be the fingerprints of holography. Future missions like the Lightbird satellite will scan this primordial glow for statistical irregularities, unexpected correlations between hot and cold spots that don't fit standard cosmic models. If the universe is a projection, these anomalies might be cosmic compression artifacts, distortions left over from translating 2D data into 3D reality. But perhaps the most revolutionary tools lie not in space but in labs. Quantum computers, with their ability to simulate systems beyond classical reach, could soon model holographic universes in silico. Imagine programming qubits to emulate the ADS/CFT correspondence, creating a tiny, self-contained cosmos where quantum interactions on a simulated 2D boundary generate emergent 3D physics. While it wouldn't prove our universe works this way, success would demonstrate the principle's plausibility, like building a scale model of a bridge before constructing the real thing. Already, researchers at institutions like Google Quantum AI are using superconducting qubits to explore how spacetime might arise from entanglement, offering tantalizing glimpses into holography's mechanics. Then there's the wild card, tabletop experiments probing quantum gravity. Devices like Bose-Einstein condensate's ultra-cold atom clouds where quantum effects dominate could reveal how microscopic spacetime pixels interact. By manipulating these systems to mimic holographic boundaries, scientists might observe how 3D properties emerge from 2D rules, like watching a shadow puppet gain depth as the hands behind it move. The challenge, of course, is scale. The universe's hypothetical 2D surface isn't some disk we can point a telescope at. It's a mathematical abstraction, likely at the universe's edge if it has one or woven into its fabric. But every great theory started as untestable speculation. Once, atoms were just a philosopher's dream, black holes a mathematician's quirk. The holographic principle's real test won't be a single eureka, a moment, but a convergence of clues, gravity's quantum whispers, entanglement, spacetime stitches, and perhaps even quantum computers humming with simulated universes, all pointing to a reality far stranger than it seems. The hunt isn't just for answers, it's for a new way to see the world, or more accurately, the shadow it casts. Leonard Susskind leans back in his chair, eyes alight with the kind of curiosity that's fueled half a century of breakthroughs. When I first proposed the holographic principle, he muses, it wasn't some grand epiphany, it was desperation. The year was 1993, and black holes were tearing physics apart. The paradox of information vanishing into their depth seemed to violate quantum mechanics' most sacred rule. Information can't be destroyed. We had two choices, Susskind recalls. Either quantum theory was wrong or our understanding of spacetime was incomplete. I bet on the latter. His voice drops conspiratorially, and boy, did the universe deliver. Cut to Juan Maldacena, the soft-spoken architect of the ADS/CFT correspondence, sketching equations on a cafe napkin. The beauty of the duality, he explains, is that it's not just a metaphor. The math works. When asked why a 5-dimensional universe with gravity could be perfectly mirrored by a 4-dimensional quantum theory without it, he shrugs. It's like discovering that a symphony and a fractal are two expressions of the same underlying pattern. You don't question the miracle, you listen. Critics initially dismissed his work as abstract gymnastics until other physicists began using it to solve real-world problems in quark-gluon plasmas and superconductivity. The universe, Maldaisner smiles, has a way of humbling skeptics, but not all voices are convinced. Enter theoretical physicist Sabine Hossenfelder, arms crossed. Holography is elegant, sure, she concedes, but elegance isn't truth. Her concern, the lack of experimental proof. Until someone detects holographic noise or finds a way to test ad s/CIVT in our flat universe, this is just pretty storytelling. She taps the table for emphasis. Science isn't about what feels right, it's about what is. When pressed on whether the principle's mathematical consistency counts as evidence, she counters. String theory has beautiful math too, and after 50 years, it's still stuck in the realm of might be. Back to Susskind, who bristles at the criticism. Sabine's not wrong to demand proof, he admits, but she's missing the point. Holography isn't just a theory, it's a lens. Even if the details shift, the core idea, that information shapes reality, has already transformed how we think about black holes, entanglement, even the Big Bang. He leans forward. Did anyone complain when Boltzmann connected thermodynamics to atomic motion, even before atoms were seen? Paradigms shift long before microscopes catch up. The conversation takes a speculative turn with physicist Eric Verland, known for his controversial entropic gravity theory. What excites me, he reflects, is how holography blurs the line between it and bit. If spacetime emerges from information, then gravity isn't a force, it's a side effect of the universe optimizing its data storage. Verland's eyes gleam. We're like characters in a video game realizing the physics engine is just code, and code can be rewritten. Finally, imagine a round table with these thinkers debating holography's future. Maldaisner envisions a day when quantum computers simulate holographic universes, proving the duality in silicon. Hossenfelder demands a smoking gun in the cosmic microwave background, anomalies only holography can explain. Susskind, ever the provocateur, jokes that the ultimate test might require jumping into a black hole. Just don't expect to tweet the results, he deadpans. What unites them, despite the debates, is a shared sense of awe. Whether holography ultimately holds or fractures under scrutiny, it's already done something remarkable, turned the universe into a puzzle so compelling, even its pieces are worth studying. And in science, as Verland puts it, the questions we dare to ask today become the textbooks of tomorrow. Let's try something. Close your eyes and picture your favorite video game, the sprawling cities, the way sunlight filters through digital trees, the weight of a virtual sword in your character's hand. Now imagine pausing the game and zooming in until you see the code. Beneath all that immersive 3D beauty, there's just lines of text, numbers, and algorithms. The game isn't actually three-dimensional. It's a flat script tricking your brain into perceiving depth. Now, stretch that idea to the cosmos. Could the universe be running on similar code, a 2D program rendering a 3D illusion so convincing we've never noticed the seams? Here's another experiment. Grab a credit card with a holographic sticker, the kind that shimmers when you tilt it. Notice how the flat surface creates the uncanny effect of depth, like a tiny galaxy floating above the plastic. That sticker isn't storing a 3D object, it's just bending light in precise patterns. Now think bigger. What if the night sky, with its swirling nebulae and distant stars, is the same trick scaled up? The light we see might not be coming from actual celestial bodies, but from data etched onto some unfathomable cosmic surface, projected into the void like a celestial laser show. Let's get tactile. Take a sheet of paper and draw a stick figure, say, a little astronaut. To that 2D doodle, you are the higher dimensional being. You can see the entire universe of that page at once, the astronaut's front, back, even the paper fibers beneath the ink. But to the astronaut, there's no beneath. Their reality is flat, limited. Now, flip the perspective. What if we're the stick figures? What if some higher dimensional artist sees our 3D world the way we see that doodle, as a surface they can observe all at once while we're trapped inside it, oblivious to the bigger canvas? Try this one hands-on. Open a word processor and type a sentence. The universe is a hologram. Those letters are just pixels on a screen, right, but when you read them, they become an idea in your mind. The information is flat, yet it conjures depth, meaning, emotion, even doubt. Now, imagine every atom in your body, every star in the sky is like that sentence. The pixels might be Planck-scale bits of information on a 2D boundary, and the screen is the universe itself, rendering not just words but the very fabric of reality. Here's the kicker: these thought experiments aren't just playful distractions. They're simplified versions of how physicists like Leonard Susskind and Juan Maldaisner approach the holographic principle, peeling back layers of intuition to expose the scaffolding beneath. The difference is they're working with equations instead of credit card stickers, and their thought experiments involve black holes and string theory. But the core idea is the same. Reality might be a performance, and we're not just the audience, we're part of the show. So the next time you swipe your phone or lose yourself in a game, pause for a second. That flicker of pixels mirroring a universe might be more than a metaphor. It could be a clue, a tiny, human-scale hint that the cosmos itself operates on similar rules. And if that's true, then the real mystery isn't whether we're living in a hologram, but why it feels so convincingly real. If the universe is a hologram, if every star, every heartbeat, every thought is just information painted on some vast, unseen canvas, does that knowledge change anything? Not just in the equations physicists write, but in how we wake up each morning, how we love, how we wrestle with meaning. On one hand, it could be the ultimate humility. The grand narratives we've built, our wars, our empires, even our notions of self, might be shadows flickering on a cave wall we can't escape. Yet on the other, it might be the ultimate liberation. If reality is malleable at its core, if the rules are just emergent patterns, then the future could be far more open than we ever dared to dream. Take morality, for instance. If free will is an illusion, if every choice is predetermined by quantum data on a 2D boundary, does that absolve us of responsibility, or does it deepen it? Some philosophers argue that understanding the universe's determinism doesn't erase ethics, it reframes them. If we're all running the same cosmic algorithm, then cruelty and kindness aren't just personal failings or virtues, they're expressions of a deeper code we're still deciphering. Imagine living in a world where every action, every law, every act of forgiveness acknowledges that we're all avatars in the same grand projection. It's a perspective that could breed either nihilism or radical empathy. The choice, ironically, might still be ours. Then there's the tension between wonder and disenchantment. For centuries, science has peeled back layers of mystery, turning lightning into electrons, life into DNA. Each revelation risked making the world feel smaller, colder, but holography flips the script. Instead of reducing reality, it expands it, not outward into space, but inward into complexity. The sunrise isn't just a ball of plasma, it's a symphony of quantum bits rendering light in real time. A lover's touch isn't just nerve signals, it's information resonating across dimensions. The danger isn't that we'll lose wonder, but that we'll drown in it, overwhelmed by the sheer improbability of being here at all. This raises a quieter, more intimate question. Does it matter if the universe is real? When a musician loses themselves in a sonata, or a parent stares at their newborn's face, the notes and the freckles aren't less precious because they might be projections. The holographic principle doesn't erase joy or grief, it recontextualizes them. Pain is no less sharp, love no less fierce, just because the stage might be made of data. If anything, it makes the performance more astonishing that chaos and beauty can emerge from such minimalist rules. Perhaps the real ethical test is how we handle the knowledge. History is littered with paradigm shifts that were weaponized from Darwinism, twisted into eugenics to quantum physics fueling nuclear winters. If holography ever moves from theory to fact, will we use it to build bridges or walls, to marvel at the connectedness of things, or to justify division by dismissing others as just projections? The answer won't be in the math, but in us, the strange, self-aware glitches in the code who keep asking why the universe bothers to exist at all, and that's the paradox. The holographic principle could be the ultimate demystification or the ultimate mystery. It explains reality by making it more incomprehensible, grounding existence in something even stranger than spacetime. Maybe that's the point. Some truths aren't meant to simplify the world, but to complicate it beautifully, leaving us breathless on the edge of understanding where science and poetry collide. Let's set the record straight. The holographic principle doesn't mean we're trapped inside a sci-fi hologram, glowing like Princess Leia's pixelated plea for help. That's the first myth to dismantle. This isn't about literal light projections or digital simulations. When physicists say the universe might be holographic, they're describing a profound mathematical relationship, a way to encode the complexity of three-dimensional spacetime on a two-dimensional surface without losing a single bit of information. It's not a claim about glowing grids or alien projectors. It's about the universe's underlying architecture, where depth and volume could emerge from quantum interactions on a boundary we can't see or touch. Another common slip-up, equating holography with solipsism, the idea that only one's mind truly exists. Some hear reality is a projection and leap to nothing is real, but that's a misreading. The holographic principle doesn't erase objectivity or imply the universe is a figment of your imagination. Your coffee cup still exists, your memories are still yours, and the laws of physics remain stubbornly consistent. The theory merely suggests that the cup's solidity, the warmth of the coffee, even the flow of time might be secondary phenomena like shadows cast by a deeper, flatter reality. Your experiences are real, they're just not fundamentally three-dimensional. Then there's the buzzkill myth. Holography proves we're in a simulation. Not so fast. Simulation theory is a cultural cousin, not a scientific conclusion. While both ideas play with the notion of reality as an illusion, holography doesn't require programmers, supercomputers, or any intentional design. The universe could simply be this way, a natural consequence of how information organizes itself at the most fundamental level. Think of it like ice forming on a pond. The intricate crystals aren't designed. They emerge from water molecules following basic physical laws. Similarly, a holographic universe might self-assemble from quantum rules we're still uncovering, no outside coder needed. A subtler misconception lurks in the shadows, that holography diminishes the universe's grandeur. If everything's just information on a flat screen, doesn't that make existence feel cheap? Hardly. Consider a symphony. Knowing it's built from vibrating strings and air pressure doesn't strip it of beauty. It deepens your awe for how simplicity gives rise to complexity. The holographic principle does the same. The fact that a black hole's fiery interior or a supernova's brilliance could be encoded on a cold, distant boundary doesn't make them less magnificent. If anything, it reveals a cosmos far more ingenious than we imagined, where the most alien phenomena are threads in the same mathematical tapestry. Lastly, let's tackle the overreach. Some popular accounts stretch holography to explain telepathy, consciousness, or other paranormal claims. That's pseudoscience hijacking legitimate physics. The theory makes no predictions about psychic powers or collective minds. Its domain is quantum gravity, black hole thermodynamics, and the fabric of spacetime, not ESP or mysticism. The moment someone says quantum holograms prove the soul exists, you've left the realm of peer-reviewed journals and entered speculative fiction. Here's the crux: the holographic principle is a lens, not a manifesto. It doesn't answer every existential question or reduce life to a glitch in the cosmic code. What it does offer is a radical new way to see the universe's scaffolding, not as beams and bolts, but as information and relationships. And that's enough to keep physicists and the rest of us wide-eyed for decades to come. What if the holographic principle isn't just rewriting physics, but also how we see ourselves? Beneath the equations lies a tantalizing question. Does a universe built from interconnected quantum data hint at something deeper, even spiritual? Ancient traditions have long spoken of unity Taoism's 10,000 things, emerging from the One, Hinduism's Brahman weaving reality like a cosmic tapestry. Now science edges toward a parallel vision, not through mysticism but math. When the holographic principle suggests that every particle in your body is tied to every star in the sky through entangled threads on a 2D boundary, it's hard not to feel the echo of those old truths. But here's the catch: this isn't about manifesting destiny or cosmic consciousness. It's about the raw mechanics of how information binds reality, and why that might feel strangely familiar to seekers across millennia. Take entanglement, quantum physics' most ghostly quirk. Two particles link across light years, their fates intertwined no matter the distance. In a holographic universe, this isn't magic, it's infrastructure. The spooky action Einstein mocked might be the universe's way of stitching 3D reality from 2D data, like a loom weaving 3D patterns from flat threads. Tibetan Buddhists describe reality as a net of jewels, each reflecting all others. Dutch physicist Gerard T. Hooft, co-architect of the holographic principle, might phrase it differently: the universe is a quantum error correcting code. Both point to a profound interdependence, one poetic, one computational, but the resonance is uncanny. Yet physicists bristle at muddying the waters. The holographic principle doesn't prove Zen Buddhism, cautions Leonard Susskind. It's a precise mathematical framework, not a metaphor for oneness. He's right: mistaking equations for enlightenment risks turning a groundbreaking theory into new age bumper stickers. But dismissing the overlap entirely misses a richer truth. Science and spirituality have always asked the same questions. What is real? How are we connected? Just with different tools. The holographic principle doesn't validate ancient texts, but it does something perhaps more remarkable. It offers a bridge, not between belief systems, but between ways of seeing. When a Navajo elder speaks of the world as a web of stories, and a string theorist describes spacetime as a network of quantum links, they're not saying the same thing, but they're standing on the same precipice, gazing into the same abyss. This duality plays out in modern labs. Researchers studying meditation's impact on brainwaves find long-term practitioners exhibit heightened gamma wave synchrony, their neurons firing in unusually coordinated patterns. Meanwhile, quantum physicists model the universe as a system where entanglement synchronizes particles across vast distances. Again, not the same but parallel, one exploring inner unity, the other outer. The holographic principle doesn't say these realms are linked, but it does suggest that separateness might be the real illusion. Not because of karma or chakras, but because reality's source code operates in a dimension where individuality is a derived property, not a fundamental one. Here's where awe walks a tightrope with empiricism. The holographic principle is rigorous, testable, and, if true, revolutionary. Yet its implications ripple into territories science isn't equipped to map: meaning, purpose, the visceral sense that existence isn't just atoms rattling in the void. Perhaps the greatest gift of this theory isn't answers, but humility. After centuries of reductionism breaking the world into smaller, isolated parts, we're arriving at a frontier where wholeness reasserts itself, not as philosophy, but physics. Not as something to believe, but to measure. So where does that leave us? Not with a spiritual manifesto or a cold equation, but with a choice to let this new vision of reality deepen our wonder without diluting our rigor. To stand in the overlap of data and mystery, where the universe's hidden blueprint invites both telescopes and poets. After all, if the cosmos is a hologram, then every question we ask, every connection we feel, might just be the universe's code reflecting back at itself, a loop as ancient as the stars and as intimate as a thought. We've traveled from the fiery edges of black holes to the cold, flat codes that might underpin reality itself, a journey stretching the limits of imagination. The holographic principle doesn't just rearrange the universe's furniture, it dismantles the house, revealing a blueprint we never knew existed. What began as a desperate fix for the black hole information paradox has blossomed into a radical reimagining of existence, a cosmos where 3 dimensions are an elaborate performance, and the real script is written in quantum ink on a 2-dimensional stage. This isn't just theoretical gymnastics, it's a revolution in perspective, as profound as when Copernicus knocked Earth from the center of the universe, or when Darwin wove life into a single branching tree. If the holographic principle holds, reality isn't a fixed, solid thing, it's a dynamic dance of information, a cosmic sleight of hand where the stage is an illusion, and the actors are pixels in the grandest image ever rendered. The chair you're sitting on, the device in your hand, even the thoughts firing in your brain, none of them lose their vividness or weight. They simply gain a deeper, stranger context. But why does this matter? Because it reframes the oldest questions we've asked about existence. Not just what the universe is, but how it is. How emptiness becomes substance, how randomness becomes law, how simplicity births infinite complexity. It turns black holes into Rosetta Stones, quantum entanglement into cosmic glue, and spacetime itself into a canvas painted by mathematics we're only beginning to decode. More than that, it humbles us. In a holographic universe, we're not just observers peering through a microscope, we're part of the specimen, our very perception woven into the fabric we're trying to measure. Yet here's the paradox, the more we unravel, the more awe replaces certainty. Every answer spawns new questions. If reality emerges from a 2D boundary, what lies beyond it? If time is an illusion, why does it feel so relentless? And if we're all just projections, why does a sunset still steal our breath, or love still crack our hearts open? Science doesn't erase mystery, it deepens it, reminding us that the universe is far weirder, wilder, and more wonderful than our ancestors ever dreamed. So where does that leave us? Not with tidy answers, but with something better, curiosity, the fuel of every great discovery. Whether reality is solid or shadow, the quest to understand it is what makes us human. We're the universe's way of interrogating itself, of turning its own code into poetry and equations. And that's a story still being written, one pixel, one paradox, one revelation at a time. Now, we'd love to hear your thoughts. Does the holographic principle excite you, unsettle you, or feel too abstract to grasp? Drop a comment below. Is reality the solid ground beneath your feet, or the most spectacular shadow show in existence? The conversation's just getting started, and in a universe this strange, every perspective adds another brushstroke to the painting. Keep questioning. Keep wondering. After all, the next great leap might begin with a single thought.